Hey everyone, welcome back and let's write some more neat code today. So today let's solve length of longest Fibonacci subsequence. Very interesting problem today. I really like this one actually. Short and sweet. The idea is we are given an array of numbers that is strictly increasing. Please pay attention to that. It's probably the single most important observation in the problem. The array is already strictly increasing. And you know what that implies, right? No duplicates. So if you are decent at Leetcode, I might have already solved the problem for you. If not, that's perfectly okay. I'll still run through the problem description, give you a high-level overview with some of the intuition of how to solve the problem, do a bit of a dry run, and then we'll code it up, and then I'll discuss the optimization, which I find is pretty interesting, and I can actually show you how to easily convert the first solution into the second solution. It's pretty much a common trick I use. A lot of people don't like that trick. For some reason, that's harder for people to understand, but I'm going to show it to you anyway, because in my opinion, it's just so damn easy once you get used to it. But anyways, so let's consider the very simple example we're given, because honestly, I think this one is enough to understand this problem and like come up with a solution. So let's say this is the input array. What we want to know is what is the longest subsequence, not subarray. It doesn't have to be contiguous. So we take like a sequence of elements from left to right. We can skip over some of them. Maybe I take that, maybe I take this, and then I take that. And so these numbers form a Fibonacci-like sequence. So the requirements of this are also important. The sequence has to have at least 3 numbers. Now, I think the reason they say that is because if they did not say that, you could be given literally any array of 2 elements. If I call it like 1,000 and I call it 2,000, I mean, you can't say this is not a Fibonacci-like sequence, provided like you know what a Fibonacci sequence is. I'll try to cover that briefly. Because if you just have 2 numbers, I mean, it's kind of like the base case. You could have any 2 numbers, but anyways. And then the more important requirement is that, like, generally the Fibonacci sequence is like this. It starts with, I think, 2 ones. And then you take these 2 numbers to get the next one, you add them together, and then you take these 2 numbers, add them together to get the next one, and you just kind of keep going, 5, 8, 13, and it just kind of keeps going like that. Now, we don't need this exact sequence. We can actually have any starting point. For example, you see a 4 does not show up in the sequence. If I start with 4, I start with 5, add these together, I get 9. This is not the Fibonacci sequence, but this is a Fibonacci-like sequence. So now I could just kind of keep going, add these 14, 23, 37, just keep going. So this is what we care about in this problem. And from this array, we're looking for a subsequence. So now if you understand everything up until this point, and now you don't know how to solve the problem, you're probably getting kind of nervous. If you were in a real interview, you'd probably start sweating. You'd probably think, okay, I don't quite know what the brute force solution even is. I mean, we're dealing with subsequences. If you've solved some subsequence problems, you know to enumerate all subsequences, it actually takes backtracking to do that. And, you know, that's a possibility. That's probably going to at least be an exponential solution. And then you're probably thinking, well, dang, then maybe I can optimize it with dynamic programming. And maybe we could get it down to some kind of like linear or n-squared solution. It might be difficult to do that. And, you know, this is not like a bad line of thinking. The hard thing about this is that this is kind of valid. Like, there's nothing wrong with this. I don't actually know if you can like take the backtracking solution and then optimize it to DP. I didn't actually do that. But when you're given a problem like this one, that's one idea I had, but I saved that idea. Like, this is how my brain works. I put that idea on hold and I wanted to explore maybe there's other solutions that are easier or more efficient. I think there probably might be a DP solution just because I've seen this pattern of problem before, Fibonacci subsequence. It seems like there might be DP. And it might be like related to the backtracking solution. But then I also asked myself, maybe there's some kind of pattern or shortcut with this problem that typically comes into like greedy solutions. And so that's the first thing that I explored. Maybe I can come up with some kind of greedy solution. I saw it strictly increasing. So maybe, just maybe, I can actually come up with something like an n squared solution, because one thing I know for sure is this. Once I pick my two starting values of like the Fibonacci, 2 and 5, at this point, every number that comes after it is already determined. I mean, I don't know if there's like an equation to calculate the ith Fibonacci sequence. There might be or not, but at the very least, I know this is deterministic. There's no probability involved or anything. Like by choosing this elements, we have determined what the next elements are going to be. So my line of thinking was this. I get a couple nested loops for I, for j, and I pick every single pair of starting elements. So like maybe for this and this, I start there, or I could start like this, or I could start like this, etc., etc. And then maybe this is my first element, and then I start here, or here, or here, and just kind of keep going like that. For that, then maybe the rest of this, I can scan through that, maybe with like an extra loop or something. And I think you could, with like another loop, just kind of determining, like keep going until you find the next number. So let me kind of just show possibly what that would look like. Let's say we started with 1, and then we started with 2 as well. Okay, now I have my third pointer. I don't know what to call it. I'll call it K. And then I have this number. It's 3. It is the sum of the two previous numbers. That's good. Okay, so now my two previous numbers are 2 and 3. So now I look at the next number, 4. It is not the sum of the next two numbers. So skip it. Okay, now I look at 5. It is the sum of the two previous numbers. So we're good. That's one solution. You might be already noticing there's a little bit of repeated work here, because we're going to kind of keep going. Like now I have 3 and 5, and then I'm going to skip 6. I'm going to skip 7, but 8 does count, so that's good. And now I'm going to try the next thing, starting from here, starting from 2 and 3. I'm going to have another pointer. Okay, 4, skip it. Okay, 5, include it. Okay, skip these two, and 8, include it. Okay, so now I found another subsequence with 1, 2, 3, 4 elements. The previous one had 5 elements. That one was the longest one. And the way I've described this solution, it's going to be n cubed. But remember, there's no duplicates. So actually, there is a slight optimization we can make here like this. Once again, I'll have like two nested loops for I and for j. I'll start here and here. And now that I know the sum of these two, all I need to check is, does the number 1 plus 2, let's call it the next number. Let's call this the previous number and this the current number. Does the next number, which is the sum of these two, does it exist anywhere? Because if it does, we already know the elements are in increasing order. We kind of already know that this is somewhat satisfied as long as the existence of the number is confirmed. So yeah, that's all we check. So how can we check that efficiently? Probably with some kind of hash-based data structure. Hash map or hash set will do. So that's what we're going to do. So then we check, okay, that number does exist. 3 does exist. That's great. So now we update the numbers. This becomes my previous, this becomes my current, and now the next number I'm looking for is the sum of these two, which is 5. I confirm the existence of it with my hash set maybe, then this becomes my previous number, this becomes my current number, my next number will become 8, and then I just check for the existence of it. So now it does exist. This has gotten kind of messy. Now my previous number is going to be 5. My current number is going to be 8. My next number is going to be 13. And we find that 13 does not exist in the array, or rather in our hash set. That's how we would do the lookup. And so if that's the case, then we can stop, and then maybe we'll try a new starting point. We have to try a new starting point because, I mean, maybe like 3 and 4, maybe somehow that can form the longest subsequence, and maybe like we had an 11 over here and something like that. So we do kind of have to check all of those, but there is a little repeated work. I'll show you how to eliminate that repeated work after I show you this solution that I just talked about. It is not quite n cubed. It's actually n squared, and like the way Fibonacci numbers work, you could kind of think of it as like two numbers that are like the Fibonacci sequence is roughly doubling every single time. Like I think it goes from 5 to 8 to 13 to 21. So you could kind of think of it as like roughly doubling, and thus you could say that like how many elements are we actually going to visit through that array? I think it's roughly equivalent to log base 2 of the, I guess you could say the length, or you could say the max number. But again, like this is a rough approximation. I think we'd have to get into a lot of math to give like a more precise answer, and I think I won't do that for this video. I don't think you'll be asked to do that in your coding interview. So let's code this one up. So the first thing I do is just throw all the elements into a set, and that will convert that into a hash set in Python. I'm also going to declare my result, which is 0. That's going to have the length of the longest Fibonacci subsequence. That's what we're going to end up returning. And so now I want to go through every pair. So I'm going to have my first index go through the entire array, except the last element, because I want to have at least 2 elements. So I'm going to do length minus 1. And then I'm going to do for j in range, starting from I plus 1. I always want this element to be after the previous one, and then going up until the end of the array, because this element is allowed to do that. That way we have at least 2 elements in the subsequence. So there's that. And now I'm just going to have a couple of variables to make this readable. I'm going to have my previous and current, have that set to I, have that set to j, and I'm going to calculate the next number, previous plus current. I'm going to say, while the next number is in the hash set, let's shift the pointers. I mean, that's like the obvious thing to do here. Let's set previous to cur. Cur is going to be set to next. Next is going to be set then to previous plus cur. But while we're doing this, we should also kind of just keep track of the length. So what I'm going to do is here, initially we have at least 2 elements. We can say our length is 2, and then every time like this evaluates to true, increment the length by 1. Once that stops, we can potentially update our result. And so this is where you might have a bug. You might think to put this statement here, result equal max of result and length. But what that would do, assuming that this loop never executed and this never evaluated to true, this would run regardless. So the result would always be at least 2, but that's actually not what they want us to do in this problem. Remember how they said that they want only Fibonacci sequences that are at least 3 elements long. So for that reason, we put this inside the loop. You could put it down here, you could put it up there. Just make sure you put this after the increment. I believe that's the whole code. I mean, you could call this a brute force solution, but I don't know if that's quite accurate, because a more brute force solution would be to use backtracking, and this is more of a greedy solution in my humble opinion. And so you can see here, it does work. It's pretty efficient. I'll show you another solution that's technically more efficient in terms of the big O runtime. It's less efficient in terms of the memory. And I think in terms of the real performance, it's actually less efficient, at least when I ran it. So back to the drawing board, and just to give you a bit of the intuition of what I'm talking about, I'll show you how to think about this problem. I don't know how in depth I want to do in terms of drawing out the entire like DP grid, because I feel like for this problem, it might actually just end up overcomplicating things. But the biggest piece of intuition I want you to recognize is when we started here and here, then we found that this was the subsequence, right? That element and that element, and we skipped some elements in between. When we started over here and here, it's kind of the exact same. If we ever get to a point where current and previous are this, or sorry, I should put previous here and current, and it's the exact same, I mean, we're just going to be repeating the exact same thing we did, except it's going to be shorter, potentially missing some elements that came before it. So at this point, you should recognize that this is dynamic programming. If you don't know what dynamic programming is, I would honestly stop watching this video right now unless you're just curious of how I code this up. You can head over to Leetcode.io. There's a lot of resources on there to learn dynamic programming. I would specifically look at some of the subsequence problems, or you could just go on YouTube, watch my video on the Fibonacci sequence. But I think that probably won't be enough. You should probably practice more dynamic programming. Use other resources if you prefer. Just somehow get a decent grasp of this and then maybe come back and watch this video. But for now, I will say that that's kind of the intuition. And so when I identify that, I recognize that we can solve this in some kind of bottom-up fashion. Maybe there's a way to do it top-down as well, but I immediately recognize that the solution that we already coded up is identical or almost identical to what we need, except we're going to do this in reverse order. Because what I can do is if I had solved this orange subproblem first, I do that first, then I come back to this problem, because at that point I will already recognize that if my I is here and my j is here, the longest subsequence we can get is going to be of length 4. So then when I come back here and my I is over here and my j is over here, and I'm asking, well, from here, what's the problem? Well, I'm going to say, okay, well, if you add these two together, then they add up to 3. 3 is at this index. And so since we're using I and j's, we're using the indexes to determine the subproblem, we might need to have some kind of mapping where we take each number and map it to the index so that then we can say, okay, now 1 plus 2 does exist. It exists at this index. And so now the subproblem I'm looking for is I'm going to take my j and assign it to I, and I'm going to take j and assign it to the index of the number that we summed to. You could call it the next number. And so now I'm going to say, well, this subproblem, what is the length of it? It's already been computed. It's 4. So what I can do is say, okay, I had one number, 1 plus dp of I, j, the new I and j, once I shift them here and here. And the result of this was that 4 that I'm talking about over here, and I add 1 to it, now I get 5. So that's pretty much it. Other than that, like I said, I'm going to iterate through these in reverse order. Instead of having my I and j initialized there, I'm going to work backwards. I'm going to put my I over here and my j over here. I'm going to find that, okay, this subsequence is of length 2. Okay, then I'm going to start at the next spot. I'm over here, my I is there, my j is going to be over here. Like I said, going in reverse order, okay, the length of this subsequence is also 2. Of course, 14, the sum of these two numbers, does not exist. So we skip that. Okay, then my j is going to be shifted over here. I got 13. Does 13 exist? Nope. So once again, this subsequence is of length 2. Those subproblem lengths will be stored in our either a hash map, or we could use a 2-dimensional grid. But either way, we'll just kind of keep going. Eventually, my I will be over here. My j over there. Okay, 13 does not exist either. Eventually we'll get, I think, to this point where my I is over here. J will be here. We'll have skipped this one. We'll just kind of keep going. Eventually we'll get here. J is there. Okay, I got these two. Add them up. It's 8. Hey, 8 actually exists for once. Okay, then I'm going to ask, with this element as my I, and this element as my j, what was the longest subsequence we were able to form? Well, this one is of length 2. So I'm going to say 1 plus 2 equals 3. Fantastic. Okay, I'm just going to kind of keep going now. Now my I pointer might be over here. J is going to start there. It's just going to kind of work its way backward. Eventually it'll get here. 2 plus 3, that's 5. 5 is over there. So now I'm going to say my I is over here, j is over there. These two add them up and you get 8. But actually, we don't need to do that. We don't need to add them up. We're just going to get the length of this subproblem, which we already stored in dp. And that'll tell us the length starting at these two elements. The longest subsequence will be 1, 2, 3. So I'll take that 3, add it to this element, and that'll be 4. And then finally, eventually, I'll have my I pointer here, j pointer here. We'll find that adding these two up, we get 3. And the result of that subproblem when I is here and j is there is 1, 2, 3, 4. So that 4 will be added to this. We'll get 1 plus 4, we'll get 5. So the downside of this is that our DP grid is going to be like this and like those elements kind of going that way. So it's going to be n squared in terms of the space. In terms of the time complexity, though, you can see that this is also n squared. So that's the improvement. We're not doing any repeated work by working through this backwards. So let's code this up now. So I'm actually not going to change or not get rid of this code. I'm going to show you how easy it is to just change a couple things. First of all, take this. Python makes life so easy. I'll never understand why people use a language other than Python. I used to be a C++ person, and then I switched to Python. It took me like 4 hours to learn it, and I never looked back. But anyways, okay, I'll reverse that. And then I'll reverse this. It'll do the exact same thing. It's just going in reverse order. And so now I'm going to do this calculation, the next calculation. I'm getting rid of length, and I'm going to get rid of this loop, but not quite get rid of it. I'm just going to change it into an if statement. And then I'm going to say, okay, if the next number is in there, fantastic. So then we can say our length is going to be this 1 plus, now let's create DP, like the thing that's going to be storing all of our subproblems. So let's make it a hash map just to make it easy for ourselves. So this will basically take ij and map it to length of longest subsequence starting from I and j. And so assuming we have that stored in here, we could do something like this using the key. So we know that the elements right now that we're starting at are I and j, but the subproblem is going to be when j becomes the first key, and then we want to know the index of the next element. So right now I'm just going to assume we have a way to do that. I'm going to call it array map. And I'm going to say, okay, pass the next value in, and that'll give us the index of that element. So now I have my 2 indexes of the 2 elements, and then this will give me the length of the subsequence starting at those elements. I take that, add it to 1, I get the length. I don't really need to do these 2 things here anymore, but I will leave this line of code right there. Now, after that's done, we can then also do this, store in DP. Let's say for I and j, and notice I didn't actually change I and j. These are the original indexes that we had. So not like this sub problem over here, but actually the original problem. And for that, we just computed the length. Actually, to make that more clear, let me initialize length here as 2, and potentially we end up reassigning it here. Any value stored in here will never be less than 2. So either it'll be 2 or it'll be greater than 2, but whatever length happens to be, we will assign it here into that. And now I think the last thing for us to do is array map. And I'm basically just going to get rid of this array set. So this lookup can also be performed within a hash map. So that's why I'm doing that. And then here, I'll just rename it to array map. And life is so easy in Python. Map a number to its index for in enumerate the array. And I believe this is the entire code, unless I'm forgetting something. Let's just run it, I guess. Very unfortunate. I put brackets around here when we wanted a hash map. This is called dictionary comprehension, by the way. It's something I cover in Python for coding interviews, but I think that should be good. And so, yep, looking over here, you can see it does work. Funny enough, obviously the memory got worse, but the runtime actually did as well. I think one way to mitigate this would be, instead of using a hash map, use a 2-dimensional array. So I'll do that. So 0 times length of array for underscore in range length of array. This is nested list comprehension. I think this is also something I definitely cover in Python for coding interviews. But okay, so now that we made this a 2-dimensional array, we change this over here. So j will be the first index. This will be the next one. Just get rid of that. And then over here, it's pretty simple. Just do I and j. And I think I'm not missing anything. So let's give it a run. And yeah, so you can see that actually both runtime and memory improved a little bit. I think it's like 3 times as quick without all the hashing going on. But still, I think this is slower than the previous solution that we had. This is dynamic programming, by the way. Anyways, if you found this helpful, check out Leetcode.io for a lot more. This was a pretty difficult problem, so don't feel bad if you struggled with it, or feel bad if you feel like I made it look easy. It's not easy. The only reason it looks easy is because I've practiced a decent amount.